In this video tutorial, we're going to be looking at our AP Physics 2 lab, electrostatic force mini lab with numbers. I'm going to provide you an example. To keep in mind, when you open up your program, you're going to get different numbers and different values. So use what you get, okay? Now, the other thing you're going to need to do is click on this link here, and it's going to open up a quick graphing program. Now, once you have your program open, you'll be able to enter in values for your independent x-axis, dependent y-axis, and the values in the table. And it will automatically title your graph and label your axes and plot your points. Okay, and then you'll be getting the numbers from the actual lab itself. So you want to make sure you have the lab open. Make sure your Google Doc file is open. All right, and let's begin. So for trial one, remember we're going to change one variable at a time. So for table one, you can see we're going to change charge 1 5 times. We're going to see how the force responds to that. So the first trial, well, that's kind of already done. So charge 1 is 3.5 nanocoulombs, and the force is 4.80 millinewtons. So 30.5, 4.8. Record that. 30.5. Oops. 4.8. Okay, now I'm going to raise charge 1 higher. Notice charge 1 went up, force went up. So 37.9, 37.9, and 5.97. Okay, and so you quickly go through and make your changes. 40.5, 60.38. 46.3. 7.29. Let's see. And then last trial, 51.2. 8.06. 8.06. And so what we're going to do is we're going to put this information, this is our X, this is our Y, we're going to put it right into the quick graphing program. So X is charge 1. So Q1 in nanocoulombs, and the Y variable is force in millinewtons. Okay, and we're going to re-enter those numbers into this to actually help plot it. Okay, so 30.5, 40.8. 37.9, 5.97, 40.5, 6.38, 46.3, 7.29, 'See, that first one was wrong there. There we go. Okay. And my last data point, 51.2 and 8.06. All right. And you can see not only is it linear, right? But if I go and it's got its title, my graph, my axes are labeled. I'm going to go to curve fit and it's between proportional and linear. If I try proportional, it does line up almost exactly with the origin. And what this tells us is the electrostatic force is directly proportional to charge one. Okay, so what we're going to do is we're going to take a screenshot, however it is you know how to take a screenshot. This is how I like to take a screenshot. All right, and you're going to come back over here and paste it. So graph one, okay, goes there. And now there's one more thing we need to do. And that's, or I'm sorry, no, we're done with that. And so now we'll go to table two. So now for table two, you can see we're going to change charge two 5 times. Okay. So I'm going to bring charge one back down to its original value. That's where it started. I'm going to raise charge two 5 times and leave charge one alone. So my first one is exactly what we have here. So it's the same 30 and a half. There we go. 30 and a half and 4.8. Okay, now I'm going to raise charge two. So now it's going to be 35 and 5.37. 35 and 5.37. I'm going to raise two one more time. 42.2, 42.2, and 6.47. 6.47. Okay, one more time. 46 and 7.06. Okay, and time 51.1 and 7.84. Okay, now we're going to recopy these, of course, into our quick graphing program. What I'm going to do is I'm going to reset this. So just all I do is do that, and I'm going to get my values reset. So this is Q2 in nanocoulombs again. This is force in millinewtons again. Okay, if we enter our values, it's 30 and a half, 4.8. 30, 4.8. Okay. Oops, sorry, wrong way, over here. 35, 5.37, 42.2, 6.47, 46, 7.06, 51.1, 7.84. Okay, and you can see again, you're getting proportional data. We'll go to curve fit, proportional. We'll take a screenshot of this. Come back over here. Okay, graph two. Okay, now we're on to trial three. So for trial three, there we go. Okay, so now we're going to change the distance. So I'm going to bring Q2 back down to its original value. And this time I'm going to change the distance, all right? I can make it bigger or smaller, but I got to change it 5 times. Okay, so 1, 2, 3, 4, 5. Yep, I can do that. Okay, so my first one is going to be a distance of 42.3 millimeters. Okay, so 42.3, whoopsie, 0.3 millimeters, and the force was 4.8. And I think I'm going to enter this in the quick graphing program at the same time, just to kind of make it a little bit faster. So on the x-axis, the independent is r, okay, and that's going to be in millimeters. It's the distance between the charges. And this is still force in millinewtons. There you go. Okay, so the first one was 42.3 and 4.8. Okay, the second one, I'll make this bigger. Okay, so now we're at 45.2 and 4.21. 45.2 and 4.21. 45.2 and 4.21. Okay, third trial, 52.9, 3.07. 52.9, 3.07. Just double check that. Yeah. 52.9, 3.07. 56.1, 2.73. 6.1, 2.73. 6.1, 2.73. Okay, now you can see that the data is climbing smaller. Now it's getting really steep. But see, as R gets bigger, F clearly is getting smaller. So this is a different kind of relationship altogether. And my final one, about 60.9 and 2.32. Okay, now to curve fits, it's obviously not going to be a linear proportional. It's going to either be inverse, inverse square, or inverse square root. So let me start with inverse. Clearly, no. The curve fit doesn't even match the data. Inverse square, perfect. In inverse square model basically drops very steep and then asymptotically approaches zero as we go. So what this tells me is that the force, the electrostatic force, is directly proportional. Well, talk about that while I go ahead and copy and paste this. The electrostatic force is directly proportional to each charge, charge 1 and charge 2. You saw that from the graphs we produced. And inversely proportional to the distance between the graphs. Okay, and so we can see that from our graphs here. Just zoom out a little bit there. Okay, so force, electrostatic force is directly proportional to charge 1, directly proportional to charge 2, and inversely proportional to the square of the distance between. And as a result of that, we have derived Coulomb's law of electrostatic force.